Welcome back, guys. Today we're going to be taking a look at piecewise functions. In our last lesson, when we were graphing absolute value functions, I told you that an absolute value function was a piecewise function and that we would get into that in a later lesson. Well, that later lesson is today. So first of all, we're going to take a look at our definition. We're told that the absolute value function y equals absolute x is defined as the piecewise function y equals absolute value of x such that the absolute of x is x when x is greater than or equal to 0, and x is negative x when x is less than 0. Essentially, when we're looking at an absolute value function, even though it looks like one continuous graph, it's actually one graph made up of two separate components or two separate pieces that have then been put together to make that function. So when we're talking about absolute value functions, each absolute value can be written in pieces with a domain. Now, specifically, when we're talking about y equals the absolute value of x, this is actually a function that's made up of two linear functions. And on the right-hand side, this part of the function is represented by the equation y equals x. And on the other part of the equation, it has a negative slope. This is represented by y equals negative x. Now, where those 2 points join is right here at the origin. That would be known as our invariant point, and that's happening at x equals 0. It's also our y-intercept. Now, if you remember when we talked about absolute value, what does an absolute value do? It takes our values and makes them positive. So if I have a negative 3 and I take the absolute value, that becomes positive 3. But if I have the absolute value of 3, it just stays 3. So my positive values remain unchanged and my negative values become positive. And so if I take a look at 0, the absolute value of 0 is just 0. So it's also unchanged. Now, if you look at the piecewise function, we have x is greater than or equal to 0 and x is less than 0. So what we're doing is we're looking at what's happening to the function, or how is the function behaving when x is greater than or equal to 0, and how is the function behaving when the graph is less than 0. Now, if you remember up there, I said when we take the absolute value of 0, it's just 0. Well, 0 is neither positive nor negative, so it really doesn't matter where we put that greater than or equal to sign, but it is a convention that we put it with the positive one. So you'll notice that I'm always going to be putting the equal to sign with the positive. We're going to treat 0 like a positive number, even though it's neither positive nor negative. Now, if we were to actually sketch a linear function of y equals x, if we take a look at how that graph is behaving, as x is greater than or equal to 0, all those values are positive. And as x is less than 0, all those values are negative. So when we flip that up, this part of the absolute value function was originally negative with the original function. And so we can talk about this as being the positive part of the graph and the negative part of the graph. And so when we're creating our piecewise function here, notice this top one is going to represent the positive part of the graph, and the bottom part is going to represent the negative portion of the graph. All right, so we're going to go through a number of examples. We'll start off with linear examples and then we'll get into quadratics. Setting up that piecewise function is going to be the same process over and over. Now, one way to do that is to sketch a graph. So if I have y equals absolute value x minus 3, I'm going to graph my original function. And to do that, I'm going to need my x-intercept. If you remember, x-intercepts happen when y equals 0. So I'm going to have 0 equals x minus 3. That means x equals 3. And for my y-intercept, that happens when x is 0. So y is going to be 0 minus 3. Y is going to happen at negative 3. So then I can draw my Cartesian plane and sketch my original graph. And I'm just going to be marking my key points. So it's not going to be a very detailed graph, but I have an x-intercept at 3, and I have a y-intercept at negative 3. And then we'll sketch that graph. Now, using a straight edge would be helpful just to make sure those lines are nice and neat. Now, taking a look at our key point here, right here is our x-intercept. When we graph our absolute value function, that will be our invariant point. And so this part of the graph here is above the x-axis, so that's the positive part of our function, and anything that's below the x-axis would be negative. Now, when we redraw that absolute value function, this part here is going to flip up, and look like that. So this section of the graph had been originally negative, so that's the negative part of our absolute value. Now, we now have two sections of the graph that are behaving in two very different ways. One has a positive slope and one has a negative slope. So when we set up our piecewise function, we start by writing y equals absolute value x minus 3, and that's equal to our two sections of the graph. So from this point here, as all of my x values are getting greater than or equal to 3, the graph is positive. And so knowing that with positive values the function doesn't change, that's x minus 3. You might want to write a positive in front of that helps. And so as whenever my values are greater than or equal to 3, the function has a positive slope of x, and the equation would be x minus 3. Now, when we're looking at the other part of the graph, as x becomes less than 3, notice we can't use that equal to sign twice. So we've used the equal to sign with the positives, and we're not using an equal to sign with the negatives. So as x is negative, or as x is less than 3, that's the negative part of my function. Well, what does an absolute value do? It takes the negative function and makes it positive. And so instead of writing x minus 3, we're going to write negative x minus 3. Notice that's in brackets, and that's occurring when x is less than 3. Now we can simplify that function down by multiplying that negative through, and so our final step here would be to write y equals the absolute value of x minus 3, and the positive part of that function, x minus 3, when x is greater than or equal to 3, and negative x plus 3 when x is less than 3. So what this is telling us is that when x is greater than or equal to 3, the function is x minus 3. When x is less than 3, the function is negative x plus 3. All right, so we have y equals absolute value of x minus 2. We're going to sketch our graph here. Finding our x-intercept, we're going to have an x-intercept at positive 2. Again, we can find that by substituting in 0 for y and solving for x. And we're going to have a y-intercept at negative 2. We're going to sketch that original graph and label our positives and negatives. This would be the positive part of the graph, and then this would be the part of the function that flips up and would be the negative part of the graph. So our key point is happening right here at 2. And so we're looking at how the graph behaves when x is greater than or equal to 2 and when x is less than 2. So writing our function, we're going to have y equals absolute value x minus 2 such that our function is x minus 2. And again, you can write that positive value in the beginning if x is greater than or equal to 2. And then the function is negative, so negative x minus 2 if x is less than 2. Simplifying that down, we have our absolute value function is equal to x minus 2 such that x is greater than or equal to 2, and negative x plus 2 such that x is less than 2. All right, this would be a good opportunity to pause the video, try the next couple examples on your own, and then come back and check your work. Okay, now taking a look at our two graphs here, we're going to start with the first function, y equals absolute value 2x minus 4. We're going to start off by graphing or sketching that graph, and we would have our x-intercept at 2 and our y-intercept at negative 4. When we look at our invariant point of 2, that again acts like our border. And so when the x values are greater than or equal to 2, that part of our graph is positive. Or you can think about it in the reverse, is that our graph is positive when all of our x values are greater than or equal to 2. Now our graph is negative when all of our x values are less than 2. So remember, we're always putting the equal to sign with our positive part of the function. So starting out, we've got y equals the absolute value of 2x minus 4. The positive part of the function happens when x is greater than or equal to 2. The negative part of the function happens when x is less than 2. So again, we just simplify by multiplying that negative through. So we have y equals the absolute value of 2x minus 4. This piecewise function is represented as 2x minus 4 when x is greater than or equal to 2, and negative 2x plus 4 when x is less than 2. So taking a look at our next function here, now we can rewrite that if we wanted to as the absolute value of negative 2x plus 6 means the same thing, it's just written in a different way. Again, we find our x and our y-intercepts. We have an x-intercept at 3 and a y-intercept at 6. But this time our graph has a negative slope. And so if you notice from our original function, the positive part of our function happens when x is less than or equal to 3. So again, we're not looking at the less than or greater than piece. We're looking at where the function is positive. And the positive part of the function is going to have the equal to sign. So our graph is positive when all of our x values are less than or equal to 3. And our function is negative when all of our x values are greater than 3. So we set up our function here again. We're going to have the positive part of the function is represented by 6 minus 2x, and that happens if x is less than or equal to 3. And then our negative part of the function happens if x is greater than 3. So again, simplifying by multiplying that negative through, we're going to have 6 minus 2x such that x is less than or equal to 3, and then negative 6 plus 2x such that x is greater than 3. All right, now moving on to our next examples here, we have y equals the absolute value of negative 2x plus 4. Now, we've been solving these so far, or creating these piecewise functions by graphing the function, but we could be asked to write the piecewise function without graphing. And essentially what we're doing is we're just taking that function and looking at when it's positive and when it's negative. So we're going to take that function negative 2x plus 4, and we're going to set it greater than or equal to 0. And we're just going to solve for x to see what values of x make our function positive. So rearranging this equation, I don't like having to deal with negative, so I'm actually going to move the negative 2x to the other side. If you didn't do that and you had to divide by a negative, you would have to remember that your sign flips. So just to avoid having to remember that rule, always move your variable so it's positive. So we're going to divide by 2 here. And I have 2 is greater than or equal to x. So rewriting that, that means x is less than or equal to 2. So if I were to sketch my graph, when x is less than or equal to 2, my function would be positive. And on the reverse of that, when x is greater than 2, my function is going to be negative. So writing that out, I'm going to have y equals the absolute value of negative 2x plus 4. And my function is going to be positive when x is less than or equal to 2. And my function is going to be negative when x is greater than 2. Now simplifying that down, we're going to have y equals the absolute value of negative 2x plus 4 will happen when we have negative 2x plus 4 when x is less than or equal to 2, and a positive 2x minus 4 when x is greater than 2. Now, again, if it would be helpful, you could be sketching these graphs to double check. We could take a look. We know that negative 2x plus 4 is going to have a negative slope and a y-intercept of positive 4. That graph is going to cross at 2. So we're going to have a graph that looks something like this. That means the positive part of the graph is here, and when the graph flips up, the negative part of the graph would be in this direction. And 2x, like our border, our invariant point. So as x is greater than 2, my graph is negative, and when x is less than or equal to 2, the function is positive. Taking a look at the next example again, we can do this without graphing. We would start off by writing our function negative 2x plus 3 is greater than or equal to 0. That means 3 is greater than or equal to 2x. Divide by 2 and we have 3 over 2 is greater than or equal to x, meaning x is less than or equal to 3 over 2. So setting up our piecewise function, we have y equals the absolute value of negative 2x plus 3. The function is positive when x is less than or equal to 3 over 2, or 1.5, and the function is negative when x is greater than 3 over 2. Again, our last step is to simplify that down. So we're going to have y equals the absolute value of negative 2x plus 3. And we have negative 2x plus 3 when x is less than or equal to 3 over 2. And positive 2x minus 3 when x is greater than 3 over 2. All right, now we're going to move on to quadratic functions, and the process is exactly the same, except this time our piecewise function is going to be made up of pieces of a quadratic function instead of pieces of a linear function. So with our first graph here, we have the function f of x equals x plus 1 times x minus 3. Now this is helpful because it's already in factored form, so I can use that information to sketch my graph. And so my key points or my x-intercepts are going to happen at -1 and at +3. And multiplying this function out, I would know that my y-intercept is happening at -3. So my original function is going to cross at -3, and it's going to come down through -1, up through 3, and my graph is going to look something like this. Now, in this case, I have two invariant points, which means I have 2 points, two different points where that function is going to change direction or change properties. And so my original function, this part of the graph is positive, so the right-hand side here is positive, so anything greater than or equal to 3 is positive. Anything that is less than or equal to -1 is positive. So I have two sections that are positive, and then this part below the x-axis is negative, and we know that that's going to flip up and look something like this. So that was the negative part of my graph. Now, before we get into writing out our piecewise function, we're going to start by multiplying out the function. So we have x plus 1 times x minus 3 will give us x squared minus 3x plus 1, so minus 2x minus 3. This will be a lot easier when we're writing out our piecewise function and having to move it from a positive to a negative. All right, so we have our function here, and we could write that as absolute value of x squared minus 2x minus 3 is equal to our pieces. Now, if we notice, we have, again, 3 pieces this time. We have a part that's less than or equal to -1. We have a part that's in between -1 and 3. And we have a part that's greater than or equal to 3. So our graph is positive if x is less than or equal to -1 and x is greater than or equal to 3. Now our graph is negative between the points -1 and 3. So we're going to have negative x squared minus 2x minus 3 if x falls between those 2 points. So if you remember back in grade 10, we talked about sandwich functions. Essentially, we're sandwiching that x value between those 2 points. So between -1 and +3, our function is negative. So we write our low bound and our high bound, so -1 and +3, and x is in between, and the alligator's eating the bigger number. Now, simplifying that down, we would have f of x equals the absolute value of x squared minus 2x minus 3, such that x squared minus 2x minus 3, when x is less than or equal to -1 and x is greater than or equal to 3, and then the function negative x squared plus 2x plus 3 when x is greater than -1 and less than 3. And again, do the best you can with drawing those set brackets. Um, the quicker I get, the less neat those brackets look. But it's really important that it isn't just a square bracket or a round bracket. It should actually look like a parentheses. All right, moving on to our next example here. We have g of x equals 36 minus x squared. Again, we can sketch our graph and use that to determine our pieces. We're going to start off by finding our x and y intercepts. So for x-intercept, y equals 0. So I'm going to have 0 equals 36 minus x squared. So x squared equals 36. When I square root, I'm going to have x equals plus or minus 6. Now for my y-intercept, I have y equals 36 minus 0 squared, which is 0. So y equals 36. So that intercept is happening quite far up on the graph. So when you're sketching your graphs, they don't have to necessarily be drawn to scale. We just have to have an idea about the shape and what parts of the graph are above or below. So when we sketch this function here, we have our two key points. Our invariant points are happening at -6 and +6. That's where our graph is going to change direction. We also know that this graph is negative x squared plus 36. So we know that the graph is opening down and has a y-intercept at 36. So that original graph is going to look something like this. And so when we take a look at our invariant points, this is where we're looking at how the function is behaving at different points. So our graph is positive between -6 and +6. Our graph is negative as x gets bigger than 6, and our graph is negative as x gets smaller than -6. So our graph is positive between -6 and +6. Notice when we're talking about the positive part of the graph, we have those equal to signs. And then our graph is negative as x becomes greater than 6 and as x becomes less than -6. So again, we're dealing with the negative part. So when that graph flips up, it's going to look like this. So taking a look at the piecewise function, we're going to have g of x is equal to 36 minus x squared. When x is between -6 and +6, the function is positive. So we have a positive 36 minus x squared. When x is greater than or equal to -6 and less than or equal to 6. And then the function is negative for the points x is less than -6 and when x is greater than 6. Now, sometimes you'll see people write or. In this case, that's not too much of an issue. Now, again, simplifying, we're going to have g of x equals absolute value 36 minus x squared, such that 36 minus x squared occurs when x is greater than or equal to -6 and less than or equal to 6. And the graph is negative, so we have a negative 36 plus x squared. Again, you could rewrite that as x squared minus 36 when x is less than -6 and when x is greater than 6. All right, guys, so that's 8 examples that you have looking at how to set up a piecewise function. Remember, when you're dealing with quadratics, you might have to factor to find your x-intercepts, but you're always looking for those invariant points. Those are acting like your borders for the pieces of the function. Graph the function, see where the original function is positive. Use that to set up your parameters for the domain. All right. Hopefully that's given you enough examples. If you have any questions, make sure you ask in class. Have a great day, and we'll see you soon.